Okay, so actually, just to start, so Ariel reminded me that I never did explain the terminology in the title. So online learning. The meaning of the word online is sort of is a in sort of the CS sense as opposed to offline or batch learning. So the other sort of common machine learning paradigm is you're just given a bunch of data and you crunch on it and output something. Online learning is for cases where information is coming one piece at a time and you have to make decisions. So all the kind of things we were talking about, you get your input, you make predictions, is the market going to go up or down, or you have to play a repeated game. Things are happening one step at a time. So I just to mention that online refers to that as opposed to on the web. So that's the just the terminology there. Okay, so what we talked about last time, so here was sort of the itinerary of the tour, and we looked last time at this nice algorithm, randomized weighted majority or multiplicative weight updating for minimizing regret, and saw how it had some nice connections to mini-max optimality, that you could play this in some game you don't understand very well repeatedly and guarantee that you'll, over time, do nearly as well or better than mini-max optimal strategy would. Because you're going to end up doing nearly as well as the best fixed strategy in hindsight against the way your opponent actually played. And then we looked at the bandit problems. This is the setting where you get much less feedback. You try something, you get feedback just for what you did. You don't know how well you would have done had you tried something else, like driving a certain way to work. You find out it took you 32 minutes. You don't know how long it would have taken had you done something else. We saw how, I talked about it in the context of a sort of an online pricing problem of, pricing lemonade. And depending on time, I might talk about some other kind of pricing problems in an online setting. So I want to now talk today about a stronger notion of regret called internal regret or swap regret and its connection to something called correlated equilibria. Okay. So actually, before doing that, let me just give a comment on two-player zero-sum games. So what I talked about last time, was if you have two players and what one player does is runs a regret minimizing algorithm like randomized weighted majority, and the other player, knowing the first one's doing that, always plays best response. Okay? Then that randomized weighted majority algorithm is going to approach the minimax optimal strategy. Because if its distributions don't approach minimax optimality, so if it's not an approximately minimax optimal solution, the other guy will always be able to cause it to get a little bit less than the value v, and the guarantee says that's not going to happen. So that's one thing. So if you play, one way to find an approximate minimax optimal solution is to play a regret minimizing algorithm against the best response oracle. Okay? But another thing you can do is you could just play two regret minimizing algorithms against each other. If you have a zero-sum game and you have each player is minimizing regret, you might ask what happens. You can't say too much about the specific distribution at any particular time. You could minimize regret and every once in a while play something crazy as long as you don't do it too often. But you can say the time average distributions for each player will approach minimax optimality. Okay, and in particular, why is that? Well, just to get, I kind of want to get it's been a while since yesterday morning, so I just want to get kind of back into thinking about this. Let's say we have two players, row and column player, they're each minimizing regret. Suppose that the row's time average strategy, but what I mean by time average is you just average all the distributions they're playing at time 1, time 2, so forth. If that's far from minimax optimality, then the column player would have a strategy that in hindsight would substantially beat the value of the game. In particular, what I mean by far from minimax is I don't mean distance in strategy space. What I mean is there's a value of the game, v. A strategy that guarantees no matter what the other guy does, I get v minus epsilon, I'll say that's close to minimax optimality. If Okay, so what I mean is in terms of the quality. So if it's not a good quality in that sense, then column would have a strategy in hindsight that substantially beats the value of the game. And that means because of the column player's regret guarantee, it must actually have substantially beat the value of the game. If it didn't do that, it wouldn't be doing nearly as well as its best column in hindsight. Because it's a zero-sum game, that means row must be doing substantially worse than the value of the game, because it's zero-sum. If the column player is doing well, the row player is doing badly. And that contradicts the guarantee we have for the row player. So you see how that works? So if you play two regret minimizing strategies against each other, their time average plays have to approach minimax optimal. Okay. So in fact, Costas had mentioned this, and I'd realized I hadn't actually said it. So I thought I'd just go through that argument. Okay, so you might ask now, what happens in general sum games? So what you'd, like to say, if you have, say you have a general sum game, maybe you have two players, maybe you have a bunch of players. Maybe it's, people, every day they drive, pick a path driving to work, and how much, time it takes me to get to work depends on, the path that you pick and everyone else picks and so forth. So if all players minimize regret, in a general game, you might ask, will the time average distributions necessarily be approximate Nash equilibrium? And the answer is no. And you can give some nice examples of this, but I'm not going to do that. But you really wouldn't expect that to be true, because as we saw from Costas' talk, it's hard to even find, even in two-player games, it's hard to even find approximate Nash equilibrium, or either exact Nash or even approximate Nash equilibrium, even given a centralized algorithm that's given the whole matrix's input and gets to crunch on it. Here we're asking for something much, here we've got two players each optimizing for themselves. If you can't, given the whole matrix, in a big computer, go ahead and find some Nash equilibrium, these guys are not, with these simple little updating rules, going to magically get to one. Okay? So you wouldn't really expect that. On the other hand, you can say the following. You can say the empirical joint distribution will be an approximate coarse correlated equilibrium. So what do I mean by the empirical joint distribution? What I mean is, let's just say two players, just because I can draw that on the board. Day one, this player plays this, and this player plays that, so we'll put a check mark there. Day two, this player plays this, this player this, put a check mark there. Day three, this. Day four, this again. Day a million. Okay, these check marks, that's what I mean, the empirical joint distribution. That, how every square is played some fraction of time. So this is a distribution over entries in the matrix. If it's k players, we got it's a k-dimensional thing. That thing will be an approximate coarse correlated equilibrium. I'll define what that is in a second. Right, and this is true no matter how many players m we have. So that is something that these things will approach. It's not a Nash equilibrium, but it's this coarse correlated equilibrium. Okay, so what is this thing? Ava talked about this a bit. I'm just going to say it in slightly different words. Okay, so what's a coarse correlated equilibrium? Okay, so what's a Nash equilibrium again? Well, if you have m players, it's m tuple of distributions, p1 to p2 up to pm, where pi is distribution for player I, such that no player has any incentive to deviate, even knowing what everybody's distributions are, right? So that's a Nash equilibrium. You're happy with the distribution you're playing, even knowing the distributions everyone else is playing. Okay. A coarse correlated equilibrium is not an m tuple of distributions. It's a distribution over joint actions. Okay? So it's not, in the case of a matrix, it's not a pair of distributions. It's a single distribution over joint actions, over entries in the matrix. Or in this case, it's over m tuples of things. Okay? It's going to be a distribution over joint actions such that, now I have to tell you what. Okay. So it's a distribution of joint actions such that, okay, good. So think of this as like a car routing service or something that you could plug your car into. And if you do that, what will happen is, any given day, this thing picks from this distribution. Say you are driver I, and there are m drivers in the world. You decide that you're going to join this service, and what this thing does is it picks from this distribution and tells your car to take route AI. Does that make sense? In other words, think of, if you're car driving, think of this as person 1, person 2, person 3, and these are paths from their start to a destination. And if you decide to join the service, you plug your car into it, and then it's going to pick at random from this joint distribution, tell you, you're player 1, so you're told to play A1. You're player 2, you're told to play A2, and so forth. Okay, and your car is going to drive on that way. Okay, so think of it as a car routing service that you could choose to join or not, such that given the two options of either opt into this service or opt out, so you could choose to plug your car into it or not plug your car into it, it's rational for everyone to opt in. What do I mean by rational for everyone to opt in? If everybody else opts in, then opting in is at least as good for you as any other single action. So you say, actually, everyone else is using this car driving service, recommender service. You could choose some particular route that you like, or you could choose to plug your car into this. And an expectation, you're going to do at least as well plugging your car into this as any other fixed route.
So once you plug your car in, are you committed to that route?
Okay, that's an excellent question. Let me get to that in 20 seconds, because that's the distinction between coarse correlated equilibria and correlated equilibria. Right, good. So coarse correlated equilibrium, if you just have the two options, you can either plug your car into it, in which case your car will go on its recommended route, or decide I'm not going to plug. I'm not going to plug my car in. I don't even get to even see the recommended route. I get to just pick my own route. It's rational to plug my car in and use that. Correlated equilibrium says exactly this thing. The difference between coarse correlated and correlated is, imagine that you get to see the recommended action and then decide, maybe I don't want to do that. If it's a correlated equilibrium, you still want to do it even once you see what your car has been told to do. I think that the way I like to think of it is coarse correlated is like, you plug in and the thing drives your car for you. Correlated equilibrium is just going to tell you it's going to give you on the screen how you should drive, and then you drive it, or you could, after you see that, maybe choose, well, I don't want to. So correlated equilibrium should still be a rational thing to follow it even once you see what it's told you to do today. Coarse correlated is before you see it, you just have two options, opt in or opt out, and on average over the distribution, you would prefer to opt in than opt out.
Which definition is the one being used in Hart's no regret theory?
Yeah, so internal regret, so we'll get to this one here. So we can randomized rate majority is not going to get you this, but we'll see that a stronger form of regret will get you this one. Yeah?
So you can marginalize that distribution over action as the marginal distribution. So it's going to be something like a Nash, right? In terms of, it's going to be marginal distribution for every player on every one of its actions. Does that marginal distribution have a particular property?
Yeah, that's an interesting question, right? So does it? That's hard. It's hard to say. It depends on the game. It doesn't in general, right? If you sort of pretend it was a product when it's not, right? So in fact, one way to think about this is, so for example, a coarse correlated equilibrium. Imagine the following scenario. Suppose that the car driving service, in order to sort of make traffic run well, every time it has to take a small fraction of people, like 1% of the people, and route them on some long route in order to make everybody else's traffic better. Okay, and so what it does is, it's a probability distribution. So, a random, say 1% of people are told to go on some long route in order to make traffic good for everybody else. Okay, imagine that's the way it works. Then that could still be a coarse correlated equilibrium. It could still be good enough when it's good that you're willing to tolerate that 1% of the time that it's bad. If you go ahead and calculate your expectation, you say, okay, if everyone else is using this, how well would I do if I did this particular route versus how well would I do if I plugged in? I'm better off if I plugged in. Okay? But it wouldn't be a correlated equilibrium, because once you see you're in that 1%, you decide, you know what, today I'm not going to use it. Okay? So, in particular, a coarse correlated equilibrium can put probability of mass on dominated actions. A correlated equilibrium can't, non-strictly dominated actions. Does that make sense? So, So because once you see it, that you're being told to do this thing, here you might say, I don't want to feel like that. Okay, so that's these notions. Oh, and so we can see, I guess I don't have a slide for it, but we can see that if everybody is minimizing regret, so why is it the case that the time average, that this empirical joint distribution will be an approximate coarse correlated equilibrium? Okay, so what do I mean by that? What I mean is, think of, we're all minimizing regret. We do this for 1,000,000 times now, and we create this empirical distribution. And now, what is this P over joint actions? It's the P that just picks a random time from 1 to 1,000,000 and picks the check mark from that time. Just picks one of these check marks at random. Okay? So we have 1,000,000 check marks here, just picks a check mark at random and tells everyone to play that way. And I'm thinking, gee, should I do that? Should I join the system where the way it's going to work, it's going to pick one of these 1,000,000 check marks at random and tell me what to do? And I say, okay, well, what is my expected gain if I do that? My expected gain is exactly, on average, how well did I do in hindsight these 1,000,000 steps? Should I instead do action 1? Well, what would that quality be? That would be, well, had I done action 1 in hindsight? So my regret in these 1,000,000 steps is exactly the amount by which I might prefer not to do this. So if I have low regret, it means that this P, this empirical distribution, is maybe not perfectly a coarse quality equilibrium, but almost. I have very little incentive to do anything else. Does that make sense? Okay, so there's a really nice direct connection that this empirical distribution, this 1,000,000 check marks, that the uniform distribution on this 1,000,000 check marks, if I say, should I opt into the system? When I'm thinking about that, it's exactly the question of how well did I do in those 1,000,000 rounds compared to how well could I have done had I instead played, say, this for those 1,000,000 rounds or that for those 1,000,000 rounds. Yeah.
So even though everyone's minimizing regret, someone could be doing much better than the best.
That's right. That's right. They could.
So will that only help you?
Yeah, it's only better because it only means I did actually a lot better than any one of them, and so I really am happier to join than opt out. That's right.
Even if my opponent might have done much better than.
I don't care. I mean, here, if other people are happy, that's fine with me. Right. That's right. So you can. Right, and there are certainly games where there are correlated equilibria and coarse correlated equilibria that are better than any Nash equilibrium. So a classic one is the Shapley game. Shapley game is rock, paper, scissors, where if you both play the same thing, you both lose, as opposed to tie. If you tie, it's a zero-sum game. But suppose you both play the same thing, you both lose. Then one very nice correlated equilibrium is the uniform distribution over all entries in which everything except for the diagonal. Okay, so in other words, uniform over all pairs in which you're not both playing the same thing. Does that make sense? So that there you're yeah. So then you're going to do better, strictly better than the fixed action. I think both of you. That's fine. Okay. Yeah.
If players are doing this in the game, and we're in steady state, so imagine they're playing X3 and their weights aren't changing.
Oh, yeah.
Then their distributions of actions aren't changing, but they're playing independently. They're not playing correlated. So they're actually playing with the marginals. The previous question.
Right.
I'm not playing with the correlated.
So right. So
you have to say something about what happens when you play with the marginals.
So right, because you're saying if you imagine that players are all minimizing regret, and it turns out that their distribution stabilize, then that will be an approximate Nash equilibrium. Because it'll all factor out. So the problem is that in some games these things never stabilize. They just go around and around, and there's no stabilization at all. So that's absolutely so right. So in fact you can good. So the kind of games where this does really get to Nash is when if they're going to stabilize at all, they have to stabilize to a Nash equilibrium because they can't stabilize to anything else. But the issue is just it may not be that these distributions just approach something and stay there. They could just go in some big cycles. That,
So you're saying that force correlated equilibrium equals Nash if the game stabilizes?
if, yeah, so if this distribution happens to factor, yeah, then it's a Nash equilibrium. Yeah.
Even if it's not stabilized, so is it, keep it on vertical equal, so just set like in
Yeah, it doesn't have to converge to anything. So the statement is just that, right, it doesn't have to converge to anything in particular. So the statement is just, if we look at the time average distribution, and you say, how good is it? So let me talk about its distance from the set, or it's actually not even distance from the sets. Let me define the quality of this thing is how much incentive do you have to deviate, say, max over players, or average over players, something like that. Yeah, but distance in terms of quality, so not distance in strategy space. So, yeah. So in other words, it could be that everyone has very little incentive to deviate, but I'm not actually, there's no way to slightly change the probabilities to make it so that people have zero incentive to deviate. I'll still call that close. Yeah.
Is there a connection between cycles that you get in distributions and like best response dynamics?
Yeah, I don't know, but it's hard to. Okay, I don't. Best response is a little weird in this context because it's deterministic. Okay, so I don't know. Okay, so let me now talk about this this more general form of regret that we'll get to correlated to it. And so, what we've been doing so far is something that's called external regret. We have N strategies. We want to compete with the best of them in hindsight. There's actually a stronger thing you can do with very similar algorithms called the sleeping experts problem or the regret with time intervals problem. I'm just mentioning this just in passing before getting to the notion I'm going to talk about. Where here you're given a bunch of strategies and you're also given some properties that days might have. So imagine driving to work and I'm given in advance that there are things called weekends, there are things called weekdays. There are days when it rains, there are days when it snows, there are days when there's construction. These may overlap. You might have a weekend with construction, a weekday when it's raining, or blah, 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 right? What I would like, let's let SI be the set of days satisfying a certain property. Okay, so S1 might be the set of weekends, S2 might be the set of Mondays, S3 might be the set of days of construction, S4 might be the set of days where it's raining. What I would like is not only over the entire time to have low regret, so that over the entire time my performance is close to the best fixed action, but also simultaneously for each of these sets. So if I just extract out the rainy days, I've done nearly as well as the best path on those days. I've done nearly as well as the best path for rainy days. On weekends, I look at my performance just on weekends, and I've done nearly as well as the best path for weekends. That's a stronger thing, because this is imagining that maybe the way driving works is on rainy days you should go this way, and on weekends you should go that way. Well, I want to be able to compete with that too. And you can do that using very, very similar algorithms that we talked about.
How do you handle weekend rain days? Split all rain days.
Oh, well, so I didn't describe how the algorithm works, but the algorithm will has to be given these sets in advance, and the log n we had before will become log of n times k. The way you're going to think about them is rather than thinking about the experts as paths, you're going to be thinking about them as recommenders that raise their hands, and there'll be a rainy for every path and every property. Like rainy days, there will be one expert that sits around and only when it's rainy he raises his hand and says, I think you should go this way. When it's not rainy, he keeps his hand down. And so you're going to think of this as a bunch of experts that sometimes they raise their hand and make predictions, sometimes they don't. And then you're going to combine them. That's the way these algorithms work. But I'm not actually going to go into it at all. I just wanted to use this just to mention this is something you can do. And then to get into this next notion called internal regret. Okay, internal regret or swap regret is like this, except SI is the set of days in which we chose strategy I. So what I want is, in the days that I chose strategy 1, if you extract those out, there's no particular action I would prefer to do better than strategy 1. In the days where I did strategy 2, there was no particular action that I preferred to strategy 2. It's a little bit weird. But, yeah, in hindsight, I look back and say, all right, let me look at all the days where I took this particular route. On that set of days, was there anything better? Okay, okay, now I'm going to experience internal or swap regret if there was. These two, internal is max over these, and swap is sum. So it's the difference in these two is, imagine there's many paths, and so every day I pick a different path. Internal regret would be low, because if I look at the set of days where I picked a particular path, there was only one of them, and so couldn't have much regret, whereas swap, you'd add them up. If you think of the number of choices as small, they're about the same. Okay. So that's this notion. It's a little funny, but one way I like to think of it is, imagine you're buying stocks. So every day you pick one stock to buy shares in, and what this is saying is, I don't want to have regret of the form. If I look back and every time I bought IBM, I should have bought Apple. That's the kind of regret I'm trying to not have. Okay. So, and formally, regret or swap regret is with respect to the optimal rewiring function. Okay. So what I want to, one way to think of it as follows. I played a game for a million time steps. What we were talking about yesterday was, I compare my performance to, what if instead I had every single time played action 1? Oh, what if instead every single time I'd played action 2? What if every single time I played action 3? I want to compare my performance to those n different possibilities. Now we're going to compare our performance to all possible ways of rewiring our past, where this rewiring function says, all days when you played action 1, suppose you played action 3 instead. All days when you played action 2, suppose you played action 5 instead. There's n to the n different ways of rewiring what you actually did, those actions, to other actions you could have done in those days. All right? It's like, when you said 3, you really meant 5. When you said 4, you really meant 7. Okay? Let's rewire that way and go through. And now I want to do nearly as well as the best of those n to the n different rewirings, which includes rewiring everything to action 1, or rewiring everything to action 2. So it includes what we've already been talking about, but just adds more. Okay? So it's kind of asking to be, I'm comparing myself to a wider class of stuff. Okay, so that's what we want to have low regret of that type. The connection, right, so if all players have low swap regret, the empirical distribution of play will be an approximate correlated equilibrium. In particular, the swap regret is exactly, this thing of rewiring or swapping, is exactly the expected incentive to deviate from the chosen action. So if you think about what it means to have low regret of this type, and you think about this correlator that's going to do is pick a random one of these check marks and tell you what to do. So suppose this car driving service picks a random check mark and tells you what to do. Your expected performance is the average over all the check marks that are at the same row. Right? Told you to do row 3. It didn't tell you which day it was. It just told you you should take path number 3. So you look at all the check marks at row 3 and you say, well, how well did I do on average on those check marks that correspond to row 3? Is there anything better I should do for that? So you see why it connects to this? Because after being told to play, to take path 3, I want to know, gee, should I really do that? Well, if I have low regret, if I don't have regret of this type, if all the days when I did action 3, there was nothing better I should do, then I'm happy to follow this recommendation even after I know what the recommendation is. Okay, so that's the connection. And I just wanted to mention that when you talk about correlated equilibrium, the correlator, the thing that's picking the check marks and telling you what to do, tells you your action. It doesn't tell you what's being proposed to the others. It doesn't tell you, oh, it was this particular check mark. Remember day 57, it was that one. Because then you might remember, on day 57 I wasn't too happy. All right? think about like rock, paper, scissors, right? If the correlator is going to say, okay, I pick this up, you play rock and you play paper, right? That's not going to work. It's not, if you tell the rock guy he's telling the other guy to play paper, he's not going to want to play rock. Right? So it just tells you your action. It doesn't tell you the other action, the other guy's action. That makes sense? Okay. It's just, this is always a confusion. I just wanted. Okay. So algorithms for achieving low regret of this form. So Foster and Vora gave a very nice algorithm for this. Hart and Moskalev, Finnegan and Levine. There's a number of algorithms for doing this. What I'm going to do is just present a method that, just given what we've talked about, I think is going to be the easiest, where we're just going to convert an algorithm for the previous kind of regret, like the randomized weighted majority, into one that does this. So I'm just going to do I'm going to use randomized weighted majority as a subroutine and just interface between that and the world. A lot like, remember, we did with the bandit problem, where we interface between the randomized weighted majority algorithm and the world, and this is going to be just a little bit different kind of interface. Okay, and here's how it's going to work. I'm not going to go through this in full detail, but I just want to give you a feel of how we can get low regret of the stronger type. What we're going to do is instantiate one copy of the randomized weighted majority algorithm, or any low regret minimizing algorithm, that's responsible. It's responsible for the regret over the times in which we played action J. So those are the n copies, one for every action, one for every path. All right. Now, at each time step, they're going to each give me recommendations. They're going to each give me distributions, Q1, Q2 up to Q1. Initially, they're all the uniform distribution. All right, because you start off the randomized weighted majority algorithm, it starts the uniform distribution. But in general, this algorithm 1 could be recommending give me a certain vector, A2 might be a different probability vector, and so forth. They're going to give me a bunch of probability vectors. We are going to then, so let's view those as a matrix. Do them as row vectors. Let me do them as row vectors. Q1, Q2. Let me just pile them into a matrix. Q. Okay. Now, we want to somehow convert that into a vector we're going to play. And what we're going to do is play a vector P such that PQ equals P. It's a little bit weird. First of all, is it even clear this exists? Right? I mean, if I got this matrix, this Q. One thing is, these are numbers, they sum to 1. These are probability vectors. So is there always a vector P such that PQ equals P? Right, so the answer is yes, there is. One way to see that is, you can think of this as a random walk or Markov matrix, where think of this as transition matrix, where if you're in state 1, you transition with probability Q1 to the other states in state 2. And so then this P is the stationary distribution of this random walk. It's the distribution, so if you're in this and you take one step, you end up in the same. That's one. Yeah. Okay. The reason we're going to, that's like a weird thing, but why are we going to play it that way? And the reason is this P has actually a really nice property. You can think of P, so we're going to play, what I mean by play P is, we're going to use P as, P1 is the probability we take action 1, P2 is the probability we take action 2, P3 is the probability we take action 3, and so on. That's what I mean by play P, right? Another thing you can imagine doing is with probably P1, do what algorithm A1 did. With probably P2, do what algorithm A2 did. That would choose actions with probability P times Q. Right? Because probably P1, I use Q1 as my vector. Probably P2, I use Q2 as my vector. Probably P3, Q3 is my vector. So then P times Q would be my probability distribution over actions. I'm setting P so that they're both the same thing. Using P directly for actions is the same as using P to pick an algorithm, AI, and using what AI did to pick an action. Oh, that's just, I haven't gotten to that yet. Right, so that's a great question. At this point, I haven't told you how the feedback's coming back to the A's, and that's just some intuition to have. It doesn't have any mathematical meaning yet. So you're absolutely right that I haven't gotten to that. Good. Right now, I just said we instantiate these algorithms. They give us distributions. We play P based on that. Now we're going to get some feedback Okay, so this is what you said. We're going to get a cost vector back, or a gain vector, whatever. We're going to vector, payoff vector back. And now we have to somehow give feedback to the AIs. And the way we're going to do that is give A1, so we're going to take this cost vector and split it up. So suppose P1 was 0.1, so P is this vector of probabilities. It might be 0.1, 0.2, 0.3, whatever. So we'll give 0.1 times C to A1, 0.2 times C to A2, 0.3 times C to A3. That's the way that we're going to give them feedback. So each AI lives in a fake world. It thinks it played Q. It thinks it played this, and it thinks it got, payoff vector this, and so it thinks its payoff was Q1 dot P1C. A2 thinks it played Q2, and it got this back, and so it thinks its payoff was Q2 dotted with P2. C is a vector. It's this cost vector, and so forth. This is going to start distinguishing. This is what's going to actually cause the algorithms to diverge, because they're getting different payoff vectors. It's actually kind of confusing. If you actually go through a little example, you start wondering if what's going to happen, because initially they give a uniform distribution. So initially P is a uniform distribution. So initially these are all the same feedback, and you think, oh, by induction it'll stay the same feedback, but it's not true. They're the same feedback, but they're not uniform. So it ends up after 2 steps they'll start diverging. Okay, so what does this do? So what the heck do I mean by AJ is responsible for blah, 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 right? So what do we know? Let's just work with what do we know. AJ has low regret. That's all we know. So let's just write that mathematically. It guarantees that what it thinks its expected gain is, it thinks its payoff, is it thinks it played according to this vector, and it got this thing back, so it thinks it got a payoff of this dot that. Summed over time. And its guarantee is that that is at least as good as the best fixed action against those vectors, the best fixed I, the best fixed action I, so I'm just pulling out the ith entry, see? T here means time, not transpose. It's just time T. The best fixed action over all the time steps, plus the regret term. I'll just put that in brackets, regret terms. I'll have to write that down. So that's all we know what AJ does. We got a bunch of these equations. What do we do with them? Let's add them up. What else can we do? But before we do that, let's just slightly rewrite this. This dot product, Pj, a number, times C, a vector, dot Q, a J, a vector. Let's just rewrite that as Pj, the vector, Pj, the number, times Qj vector dot C. Okay? Dot product is commutative. We can pull out the number. Okay, fine. Now let's add up. Add up over all the algorithms here. What you get is, if I add up these guys here, okay, so it's Pj, so it's P1 times Q1 dot C plus P2 times Q2 dot C. Add them all up, you get P vector times Q matrix times C column vector, because that's just P1 times Q1 dot C plus P2 times Q2. So it's this thing here. Add up these guys, it's sum over J, min over I. Now, here's the nice thing. This is actually our total cost, because we played according to P, which is the same as P times Q. So this is just the same as P. So this is P times P is a row vector. I did P, row vector, matrix, column vector. So this is PC. This is our cost, summed over all time. This is our cost. What is this? This says for each j, you can pick the best I for that j. For each j, pick the best I for that j. Move all, what is this? This is saying take all the probability mass you had on j and pretend instead you were playing I. Because pj times ci means, what is pj times ci? Ci is the cost of action I. Pj is the probability you had in action j. This is saying, suppose that you took your probability mass on j and moved it over to I. So it's the probabilistic way of saying, when you played action j, instead play action I. Take all your probability mass of j and put it on action I instead. If you did that, if you took your probability on action j and moved over to action I, you would pay pj times ci for that, because you're paying ci, not cj. And so this is saying for every j, you get to pick the best I. And so that's, for each j, we get to move our probability to its own I equals f of j. And the i's can be different for different j, because it's a sum over j min I as opposed to min I sum j. So external regret would be the other way around. the best fixed eye in hindsight. Now we get to pick different eyes for different shapes. So that's how we get low regret of this type. Okay. So good. So we can get this kind of regret also, and this gets this correlate equilibrium.
So what happens if you consider regret with respect to simple strategies that only depend, for example, on last period's action, on last fixed number of periods actions?
Yeah, that's a good question. So let's see. So there's two kinds of things. So an easier question you could have asked, which I could answer more easily, would have been, suppose I care about different strategies, don't depend on my actual behavior, but depend on properties of the world. So basically I've got, paths I could take, plus I've got, various other algorithms that, based on factors of the world, are recommending other things. I could just incorporate those as new pure strategies. But you're saying you want things that actually depend on my past. And I don't know the answer to that. I don't know the answer to that. It's a good question.
Because you're also going in the direction of correlated equilibrium, because that's actually just kind of a total representation applies, but not really, because we're not free to choose.
Right. So, I mean, there's a certain sense in which you can't do much better than this kind of regret, but it's a I don't know the answer to that. We'll talk offline. Okay, so so at this point we've kind of finished a certain kind of line of discussion. We looked at this randomized weighted majority algorithm. It's very simple. Minimizes, says if I run this thing, I'm going to do nearly as well as the best fixed strategy in hindsight, so I can use it to play a game I don't understand very well. I'll never do much worse than minimax optimal, say if it's a zero-sum game, and I might do a lot better if my opponent's not very good. And if it's not a zero-sum game, maybe we're all minimizing regret. We'll approach coarse correlate equilibria. We have the stronger notion, internal regret or swap regret. And if we all minimize that, which we saw we can do, then the empirical distribution will approach correlate equilibria. And so that gives a kind of a very nice. So okay, good. So what's kind of neat about this is that, on the one hand, Nash equilibrium, it's a very nice, clean concept, but it has this issue that, at least in some cases, it can be computationally very hard to find. And even in cases where it's computationally not hard to find, it's still, if it's computationally hard to find, it's not going to be easy for people using simple adaptive learning rules to magically get there. And it can be worse than that. It could be that computationally it's easy to find centralized, but still people aren't going to get there adaptively optimizing for themselves. I mean, we really want, we really like, in talking about an equilibrium, is something that, people doing natural things for them. What you'd like them is to be the natural result of self-interested behavior, right? And so what this says is that coarse correlate equilibria and correlate equilibria have, in a certain formal way, we can think of them as the natural results of certain kinds of well-motivated individual behavior, okay, for certain definitions of what we mean by well-motivated, like minimizing regret or minimizing internal regret. So I think so that's kind of what we've done, and then now in certain kinds of games, though. So this is sort of in general. Now, if you start looking at certain classes of games, then the world can get nicer. For example, if you look at potential games, then they have the property that best response dynamics will approach a pure strategy Nash equilibrium. So in those games, you can say that Nash equilibrium, pure strategy Nash equilibria are a natural result of well-motivated, simple adaptive behavior, because best response dynamics will get there. Yeah.
So what happens if you use these dynamics in a potential game or a game that happens to have all the potential clusters?
Yeah, it's a little funny because these are simultaneous moves, right? There you go. Yeah, that's right. That's right. So it's yeah. I was thinking if there's a good. So you could absolutely go through that to say, well, we know it's going to approach correlated, and then we can understand what they look like in those games. Right. So what I wanted to do now is talk about some. I want to go in like a different directions because I have like 40 minutes, and we talked a little bit about pricing. Kind of thinking about bandit algorithms is one way of doing sort of adaptive pricing, say for a lemonade. And I wanted to look at just a generalization. This is going to look less like learning and more like just an algorithm problem, kind of an algorithmic pricing problem. And then I'll talk a little bit about trying to guide dynamics to better equilibrium. So in cases, we're talking about getting to some equilibrium. If you're in a scenario where there are multiple equilibria, and some might have much better social welfare than others, and you as kind of an overseer of this system kind of are observing that the world is kind of stuck in some bad equilibrium, are there, what are some ways of talking about how you might try to nudge that behavior out into better equilibrium? There's been a lot of work on that in different contexts, like maybe in a driving setting, charging taxes on certain things, like some work that a number of people have done. Tim has some very nice work on that, but I'll be looking at sort of a different thing where what the central kind of overseer can do is it can sort of recommend some things, it can advertise certain behaviors, have a small fraction of people will pay attention, will try it out. You say, really people should stop smoking, or people should do this, or whatever it is. Some small fraction of people will do it, and is that enough to kind of get everybody else to do that too? That kind of a thing. Okay, so those are sort of two directions I want to do a branch. So, so I'm going to talk now about sort of pricing. So I'm going to talk about pricing multiple goods under combinatorial valuation. This is going to be just this totally different problem. Okay? So I want to look kind of back to our lemonade stand. So remember with our lemonade stand, we were selling lemonade, trying to make a lot of money. We had, and there we had one good we were selling, which was lemonade, and we had people coming in one at a time. They each had a valuation on our lemonade, and they might buy it or might not, depending on the price we're charging. As opposed to a typical auction setting, it's not like we have one cup of lemonade. We have lots of lemonade. We can make it for free, or we have maybe some cost to make it that's subtracted out of everything. Okay, so I'm thinking of that kind of a problem. Right, so instead of a lemonade stand, think of a supermarket selling multiple goods, orange detergent, expo tickets, whatever it is. And kind of in the spirit of what Ava talked about, I want to think about mechanisms that must be very simple. They are going to be required to just assign prices to items. They're not allowed to give some sort of, it's not going to be, you submit your valuation function and we do something like that. All they're allowed to do is they assign price to items. Somebody walks in, they buy something, or they don't buy, they go out. We're allowed to change the prices, but all we can do is assign prices to items. So it's this requirement of simplicity. And our goal is going to be to maximize revenue, so we would like to make money. And I'd like to do this without making distributional assumptions on the buyers who are coming. So because of that, we're going to be forced just to get some sort of fraction of the amount of money we could possibly make. So it's going to be like what we've talked about in the sense I don't want to make it a distributional assumption. It's going to be some kind of unknown sequence of buyers, and I would like the revenue I make to be comparable in some way to the revenue I could have made had I known in advance what that sequence was, like the best fixed price, for example, or things like that. Okay, so if the customers had added valuations over oranges, detergents, expo tickets, whatever it is we're selling, we could just treat this as n different, we have n goods, we could treat this as n different single item problems. We could have our lemonade stand, our orange stand, our detergent stand, our expo ticket stand, all separate. They each adjust their prices, just split it out. Okay, but we're interested in what about more general cases? What if customers have more general kinds of valuation functions? They might have a particular set of items they want. They have a shopping list they were given to by their spouse, and they have to buy that set of things, or they, maybe there are substitutes, maybe, they don't really care what kind of fruit they get as long as they get 3 different kinds or whatever it is. Okay, so what I want to do is start with the case of single-minded valuation, so everybody has a shopping list, so every customer I has a shopping list and a value on that list, and they will only buy if the total cost of all the items in their list is at most that value they have. Otherwise, they will go to the competing store or something. So they have, each customer has some list and some maximum amount they're willing to spend. And so in that sense, they're like our lemonade buyers who, had a particular number, how much they were willing to pay on lemonade. Here they have a shopping list and the amount they're willing to pay for the list. What's going to make this more complicated, though, is that we are required to assign prices to items. We're not allowed to assign prices to lists, for instance. I'm going to look at an even more special case, just because I think it's a very fun algorithmic question with a nice open question, which is, what if all the lists are size 2? Everyone has a shopping list of 2 items. You'd like an apple and orange, I'd like an orange and some laundry detergent, whatever it is. Okay? Yeah. Okay. And so here, even the purely algorithmic offline question, by offline I mean you get all, you know your customers precisely. You know all your customers. You could think of, say we do have a distribution and we know it, or we have a specific set of customers, we know exactly what they want and how much they're willing to pay, and all we need to do is figure out what's the best price. Okay? Just the algorithmic problem of doing that, even that is not so easy. So let's take a look at that. Because we can think of that as a kind of acute problem of pricing vertices in the graph. And so, in particular, we can think of it as a following problem. Think of a multi-graph. This graph is going to have vertices that represent items and edges that represent people. Because every person wanted 2 things, so you can think of them as an edge between the 2 things they want. It's a multi-graph because maybe several people want the same pair of things. Multi-graph just means you ought to have multiple edges between the same pairs of vertices. Every edge, that's a person, has a value, VE, on that edge. Okay, so here's an example. Got item, 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 item. These are different things, oranges, apples, detergent. This person wants an orange and an apple, and they're willing to pay 10. This person wants an apple and a thing of detergent, they're willing to pay 15. What we want to do is assign prices on the goods. To maximize, so non-negative prices on the goods, to maximize the revenue we make. So how much money do we make? Well, every person, they check to see if the 2 goods they want is less or equal to the value amount they're willing to spend. If so, they buy those 2 and we make the sum of those 2. We don't make how much they're willing to spend. We just make what we're charging. Does that make sense? So if we assign these prices, this is not the best set of prices. This person who is willing to pay 40 will pay 35. This person is willing to pay 10 will go away. This person is willing to pay 15 will pay 15. This person is willing to pay 20 will pay 15. Does that make sense? That's okay. So the problem, here's just the purely algorithmic problem. I give you a graph, maybe multi-graph, with numbers on the edges. Your goal, assign numbers on the vertices to maximize the sum here, the amount of money you make. The sum over all edges such that the 2 endpoints are less than or equal to the value, so not this edge, like this guy here, of the sum of the 2 endpoints. So that's an algorithmic problem. Kind of interesting to think about. It's NP hard. So we could try to approximately optimize this. Now, approximately optimizing this is a little bit confusing at first. So I think it's, let's think of an easier problem. Okay, so we're going to try to get an approximation ratio. So what if the graph were bipartite? It'll be simpler that way. So what if the graph were bipartite? Okay, so I like to think of this as you got a restaurant that sells food and drinks, and everybody wants 1 food item and 1 drink item. And there's some optimal price to put on our menu for the different food items and the different drinks. And we're just going to try to get a factor of 2, get at least half of the optimal. Okay, and I claim this is not so bad. It's still NP hard, actually, even for bipartite graphs, which is weird. Most things on bipartite graphs. No, it's not true. I take that back. There are lots of problems that are hard in bipartite graphs. Okay, and this is one. Okay, so, but it's still hard. So, but we can get a factor of 2. Can we see how to do that? One way I like to think of is, you think of the restaurant, so the optimal, if you go ahead and ask the restaurant manager, do you make more money on your food or more money on your drinks? They're making at least half on one or the other. Right. Yeah, so what we can do is the following. Say, suppose that this restaurant, the optimal restaurant, was making at least half its money on drinks. We don't know which is the case. We'll just try both possibilities. Suppose the optimal set of prices makes at least half of its money on drinks. If you set the food prices to 0, that would still make at least half, because all the people that bought before will still buy now. Their preferred bundle is only cheaper, and maybe new people will buy. So if the optimal solution makes opt-L from food and opt-R from drinks, and we just set the prices on the left to 0, that will make at least opt-R, because all the people that previously bought will still buy, and maybe some more people will buy. So there exists a solution that makes at least half of optimal, in which one side is all zeros. And we can find the best solution of that type. Algorithmically, that's an easy problem now. If we set all the prices on one side to 0, we can now separately optimize these prices, because the set of people who want this item is completely disjoint from the set of people who want that item, is completely disjoint from the set of people who want that item. And so optimizing individual, that's easy. All we have to do is draw this curve, number of people willing to pay a particular price versus price, and just find the price that makes us the most money. Say, this price, this many people are willing to pay it, we'll make this much money, and so, we make this much money. Okay, so that we just sort people by their values and just pick the price such as the number of people below that times the amount of, number of people below that times the amount of money we're going to make is, I had my axes mixed up, times the amount of money we're going to make at that price is as much as possible. So that we can do. Okay, good. So factor of 2. So now, how can we use that to get a factor of 4 for a general graph? It's interesting to think about that. We will set stuff to 0, but we're going to reduce to that point. So suppose I take a general graph that's not bipartite. Oh man, it's not bipartite. So what do? I'm going to just flip a coin for every node and put it on the left or right side. Some of the edges will go this way, some will stay on this side, and some will stay on that side. If you look at the optimal pricing, an expectation, if I flipped a fair coin for every node, an expectation, half of its money is coming from the edges going this way, right? Because any given edge, if I flip, all I got to do is, if I flip a coin for each node to put it on the left or the right side, any given edge, 50-50 chance, it has one endpoint on the left and one endpoint on the right. So if you look at where the optimal pricing it's making its money, an expectation, half of the money, if I do this, is coming from people who want one food item and one drink item. So let me just try to make half of that. Okay? So all I'm going to do is take this graph, randomly call every item food or drink, and just try to, and now I'll run the previous thing to make half of the amount of money I could make from people who want one food item, one drink item, and on an expectation, half of the money that was to be made overall was from people who want one food item and one drink item. So I could lose a factor of 2, lose another factor of 2. Right? It's a really easy factor of 4. And just one last thing, so you might ask, can you beat this? And the answer, that's a very nice open question. Okay, there's been a study of simple, special cases of this. What if there's only high and low values, things like that. But it's not known how to beat the factor of 4.
So is it supposed to improve at least a bit if you're trying to maximize the size of the cut?
It's interesting, right? It's a natural thing to think about, because you could think of this in some sense as a factor of 2 max cut algorithm. The issue is the following. The true value of an edge is not the number on it. It's the amount of money that the optimal pricing makes from that edge. And we don't know what that is. Right? So we're trying to maximize cut for edge weights that we don't know. So at least by doing randomly, we get half of whatever that is. If we knew how much money the optimal pricing would have made from each edge, then that would... That's a great question. Oh, you can make this deterministic. This is only requiring pairwise independence. And yeah, so you can do this deterministically. It's just, yeah.
Question on the algorithm you're using. Put on the right or left. How are we guaranteed that we have this price, two things on the right, too high, so that between them,
Oh, that's fine. So we're in some sense here, we're willing to assume that we make no money at all from people who want two items on the same side. I mean, even worse is on the other side, where we're giving both of their items for free. We're making nothing. Oh yeah, yeah. Oh yeah. This is not like a requirement. I'm not requiring that that this be true for everybody. Oh yeah, yeah. So the way to read this is this is the sum over all the edges having this property, but it's not a requirement on prices. I'm not requiring the prices to make everybody happy. Absolutely, absolutely. Yeah, that's good, very good. So. Right, so I think it's a nice question. What if, now so far we've been saying we have everybody up front. What if we don't have everyone up front? They just come into our store. Let's go back to this problem of inputs that come in online one at a time. Somebody comes into our store, they buy, they don't buy, we get to adjust our prices, someone else comes in, they buy, they don't buy, and so forth. You know, can we do, performance compared to the best fixed prices in hindsight? What we can do is use the fact that the algorithm we've been looking at basically converts the problem into n over 2 separate pricing problems. Because what it does is it does this left and right, sets a bunch to 0, and then just separately prices the others. And so we can just run n over 2 separate expert or bandit algorithms, and with the regret guarantee end up doing nearly as well as if we had run the previous algorithm knowing the customers. So we can use the technology we've just developed to convert this algorithm almost automatically into one that can adjust prices as people come one at a time. Oh, if they tell you what they want, then you could use this one. If they don't, then you would have to use the bandit one, the one that just gets the less information. When they buy, we know what they want. When they didn't buy, when they don't buy, yeah, then you'd end up not knowing. Yes, this is a little bit not. I'm hiding a few things under the rug here. Like, what do you do? What feedback do you give those algorithms? Someone comes in, they look, and they walk out. Like, which ones do you say got to pay off with 0? So you do have to do that right. I'm just, yeah. Good. And so now this is okay. So I just want to mention one thing. So you might ask, is it incentive compatible? So that depends a little bit on your model. If you want to talk about incentives, then here you need to assume that people aren't able to control the time at which they arrive. They arrive, they can buy or not buy. They're not allowed to wait around because prices are fluctuating, so they can't just hang out and wait for the prices to go down. They come, they can buy or not buy, and they leave. They don't return, all that kind of stuff. But you could apply this to the offline, namely the batch, everyone at the same time, incentive compatible setting, with a very simple thing. If everybody was available at the same time, you say, please write in an envelope what you want and how much you're willing to pay. Seal the envelope. I collect the envelopes, I put them in an arbitrary order, and I just open them one at a time and run this algorithm. Right? If I'm going to do that, you might as well put what you really want in the envelope, because when it gets to you, it's being opened up. Your value and items are being compared against the prices, and you're buying them if those prices are less than or equal to your value. So you might as well put down what you really want. Right? So you can immediately convert this into an incentive compatible mechanism for the case when everybody's up front. Okay. The one case where this is not incentive compatible is if you have people who can kind of delay, they could hang around and wait for prices to go down. So for instance, there are settings where you might want prices to say only go up or something, so that people have no incentive to wait around or things like that. Okay. Okay, this is pairs. What about more general valuations? So what if people have bigger shopping lists? Or what if they just have, arbitrarily complicated valuation functions? Like, they have a valuation function in their head of overall 2 to the n possible bundles of how much they're willing to pay, and they're quasi-linear. So they want to buy the bundle that has maximized their value on the bundle minus the price.
Why do we need the approximation algorithm formulation in order to use our regret learning?
Right. So the way that this is going to work is we are going to randomly Okay, so the question, right, so what we're going to do here is randomly assign each vertex left or right, take the ones on the left, give them price 0. The ones on the right, we're going to instantiate a bandit algorithm for just pricing those. So we'll just have a bunch of separate bandit algorithms. Some people are going to want that item or not. If somebody wants 2 items, they're both being priced, we'll just pretend that's 0 because that's, so they're going to come in and we're going to update that. Now, if we weren't worried about computation, you could instantiate a separate expert for every possible price vector and then go ahead and do that. So it's just that then there'd be a lot of experts. Now there's this logarithmic penalty, so that's good, but computationally it would be too painful because we'd have one expert for every possible vector of prices over all items, just be too much. So that's one. So I wanted to mention just, so it's natural to then ask, well, gosh, what if people are, what if we don't want to make assumptions about people's valuations, but we still have to assign prices to items. So here, you can still get something. Not as good, but you can still get something. You get a log factor approximation. A log of what? Number of customers times number of items. You could ask yourself whether that's good or, is that a good thing or not a good thing? But anyway, it's a log factor by a very simple algorithm. So in some sense, it's kind of a, it's not a, we're not getting, 90% of optimal, we're not even getting half of optimal. We're getting a log factor of optimal. But we're not making assumptions. It's people with arbitrarily complicated valuations, and we're not making any distributional assumptions about them. And the algorithm is going to be incredibly simple. The algorithm is going to be, so I am going to make one assumption. I'm going to assume a bound. So it's sort of the Bill Gates thing, right? You need to assume some bound on the valuations. Actually, we needed that even before with the, in the online setting. So all the valuations are between 1 and h. So h is the highest amount that anybody wants to pay for, or anybody is willing to pay for any set of things in the store. Okay, so it's the max for all I, that their value, the maximum value of the subsets is at most h. And furthermore, that there is, what I want is that h should be known, and there should be at least h amount of money, at least h amount of total social welfare in there. Yeah, so so we are told a value h with 2 properties. We're told that first, nobody wants to pay more than $1,000 coming into our store, and secondly, this whole set, if you add up over all the people, there is $1,000 worth of total social welfare to be had. Okay. The algorithm is going to be very simple. It's going to pick a random single price and just price all the items at that price. The random price is going to be a random power of 2, h over 2, h over 4, down to h over 2 and m. So it's a random single price. So a lot of nice results about these sort of simple algorithms, and I'm going to show you a result for this setting. So very simple. The claim is this will get you the log factor. Okay, so the theorem will be that the revenue is within a log factor of the maximum possible social welfare. So this is actually comparing to a higher benchmark. So in some sense, the benchmark here is the total. So if you gave everything away for free in your store, how much total happiness would there be in the world? I would like the amount of money I make to be within this logarithmic factor of the total amount of happiness there would be in the world if I gave everything away for free. Okay? That's the statement. Right, so how to analyze this? So okay, first of all, everyone know, okay, algorithm makes sense? Simple algorithm, pick a random price. It's like the dollar store, except we, rather than charging everything $1, we pick a random number and charge everything that. Okay? Right. Okay, so since we're assuming our goods have 0 marginal cost to us, we can just focus on a single customer and see what happens to a single customer. Then we'll just add up over all the customers. So what I want to do is pick one person and analyze a kind of a demand curve for that one person. So just think of one person. This one person is a very complicated valuation function. It's this complicated object, and I want to summarize that person in a simple curve. Okay? So that makes sense. So this one person has a valuation function. We have n items. There's 2 to the n possible subsets. They have some arbitrarily complicated valuation function subject to their values lying in this range, or lying h or smaller. And actually, I don't think you need the 1, just less than or equal to h. What I mean by the demand curve is the following summary. It's, if I were to price my goods at 0, how many items would they buy? They might buy everything in the store. Oh, I'm assuming that everybody wants at most 1 of any given item. Okay, so the setting is like they can either take an apple or not, take an orange or not, take a pear or not. So there's okay. So they could take 1 of each. Could be all n. It could be there's certain items that I'm selling in my store, like toxic waste, they prefer not to take. Okay, so it doesn't have to be all n of them. Their values, so they can have negative values on items. It's okay. And now, as I start increasing the price, remember there's going to be one number, which is the price I'm putting on every item. As I increase that from 0 up, they might want to buy fewer and fewer items until finally my price is so high they don't want anything in my store. And that's what this curve is. How many items would they buy as a function of the price I'm selling the individual items at? Right, so this is items purchased versus price. And the first observation here is this curve indeed kind of looks like this. It's monotone, non-increasing with price. The number of items they want starts high and it drops, okay? You can kind of, so it makes a lot of sense, right? And you can see why it's true. If at a certain price, there's a set of size 5 I prefer to a set of size 4, at a lower price, I only even more prefer the set of size 5, set of size 4, because it's cheaper, because it was 5 times that price as opposed to 4 times the price, right? So if I prefer a big set to a small set at one price, I even more prefer it at a lower price. Okay, so this curve looks like that. Good. That's number 1. Number 2, this curve has the interesting property that the integral of this curve, the area under this curve, is exactly the happiness of this person when everything was priced at 0. When everything was priced at 0, they purchased their most preferred bundle, and this is how happy they were because it was 0 price. I'm assuming they're quasi-linear, that their happiness is value minus the amount they spend. Okay, and that's exactly the integral of this curve. And you can see that as follows. You can say, let's just track the person's happiness as I start the price at 0 and start adding. If the price is 0, their happiness is exactly this quantity here. If I price everything at 1 penny, they still buy the same set of goods, but they just pay 1 penny times n0. If I price at 2 pennies, they still buy the same set of goods, but their happiness is dropped by how much they're spending, which is 2 pennies times n0. Until finally I end up charging P1. Okay, at that point, they're still buying the same set of goods, the same N0 set of N0 items, but now their happiness is dropped by the amount they're spending times the amount of items they're buying. So their happiness is dropped by exactly this area. At this price, they are now indifferent between that set of N0 things and some other set of N1 things. So let's just suppose they instead buy the set of N1 things. Their total happiness has not changed. As I now raise the price, their happiness is dropping by exactly the additional amount they're having to spend, which is this much times that. Right? So as I raise the price, their happiness is dropping by exactly the area that I'm sweeping out. So by the time I get to price P2, their happiness is dropped by exactly this much times this much. Until we get to here, where they're now indifferent between this set of N1 goods and this other set of, say, N2 goods. And now we just keep going. Okay, and as we keep going, their happiness is dropping by exactly the area we sweep out until finally at this price, they come in, things are too expensive, they buy nothing, their happiness is 0, and so the amount their happiness is dropped is exactly the area under this curve. Okay, so the area under the curve is exactly the total happiness, total social welfare for this one, maximum social welfare for this one person. So that's great. So now, going back to the algorithm, what is this algorithm doing? I claim that a random single price gets a log factor this an expectation. Why? Well, let's look. We could price at h over 2, h over 4, h over 8, and so forth, as we picked one at random. If we price at h, we sell, I guess for this person, 0 goods at h dollars, we make 0. Okay. If we price at h over 2, we sell this many things at this price, we make this much money. If we priced h over 4, we would sell this many goods at this much and make that much money. If you add up the areas of these rectangles, I claim that gives you at least half of the total area under the curve. Because see, this rectangle can pay for itself plus this part. Because remember, the curve only goes down. Right? So this area is at least as much as this area. This area is at least as much as this area. That area next one is at least as much as that area. If you add up all these things, it's at least half the area under the curve. Well, at least half the area under the curve, we stop at some point, minus this little tiny sliver here. That little tiny sliver, though, is tiny. It's this much times m, so it's only h over 2m. So it's only h over 2m for this one person. Even if you add up over all the people, it's only h over 2. And that's why I had to assume there was some amount of total money to be made, so that if I delete these little slivers, it's only a small fraction of the overall. So if I pick a random price in this range, okay, so another way to say that is, I need to assume something about the total amount of money there is to be made in order to allow me to stop at this price. I don't want to keep going down. 10 cents, 5 cents, 2.5 cents, 1 1/4 cents. I don't have to keep going down to millicents, microcents, and so forth. Okay. So a random price gets a log factor in expectation, right? Because some of the areas of the rectangle is at least half the area under the curve to the right of that. Good. And then we just add up over customers, so this random price. Oh, if the sum is half, then there's only log. Oh, where is the log coming from? I said the sum of the areas of the rectangles was half the area under the curve. How many rectangles are there? 1, 2, 3, 4. There's log of 2 and m rectangles. If the sum is half of the total area, a random individual one expectation is 1/2. What am I saying? If there are log of 2 and m total rectangles, I pick one at random, and expectation, its value is 1 over a log 2 and m of the sum. Right. Okay. Good. So the sum was at least half, so a random one was 1 over log. Okay. Good. The algorithm's clearly incentive compatible and online, because what does it do? Picks the price, just uses it. And what can you do? Come in today, come in tomorrow. I mean, all you can do is buy or not buy. I mean, it's not really. What is it? There's no haggling. It's just prices. Okay. Okay. So. So I guess the point there is kind of you can, so in these settings, we're not able to get, say, no regret or vanishing regret compared to the best you could hope to make. But we can get some things. So without assuming anything about distributions or and so forth, there's an arbitrary sequence. We can get some things, some factors. And in the case where they had shopping lists of size 2, we were able to get 4 approximation. In the case of general evaluations, we got a log n. You can get in between for the case of shopping lists of size k. Okay. So now I just want to just say a little bit about a kind of a so very sort of different question, but just related, going back to this whole issue of sort of learning and games. Yeah. So, we talk about converging to some equilibria. If we have games with a big gap between their best and worst equilibria, then can we talk about an overseer trying to guide the behavior to good state? So as I kind of showed on the slide before, this kind of is branch. So this now has nothing to do with what I was just talking about pricing, but more kind of before. I just wanted to talk about 2 things that were kind of related to the first, to what we were talking about in terms of regret. So just to give an example of a kind of game that might have that has both good and bad equilibria is the fair cost sharing game. I wasn't. Ava, in your second talk, did you talk about fair cost sharing? No. Okay. Okay. So fair cost sharing game is sort of the opposite of the routing with kind of increasing congestion game. It's a congestion game, but it's like routing where you want other people to be on your path. So fair cost sharing is you've got a communication network and everybody wants to get from one place to another, and but you get to share the cost of edges you use with other people using the edge also. So you would like to sort of have a single trunk that a lot of people use because it's cheaper. You can all split the cost of that, as opposed to kind of driving where you sort of would prefer to spread out and not all use the same thing. These games can have good equilibria and bad equilibria. A simple example is two nodes. You got one edge of cost 1 and one of cost n. A good equilibrium is let's all n people split the edge of cost 1. A bad equilibrium is let's all n people split the edge of cost n. Right? You can see, right, if n people splitting the edge of cost n, you each pay 1. No individual person has incentive to deviate to pick up that edge of cost 1. Okay, but it's really, we're all paying n total, where we could have paid 1 total. 1 per player versus 1 over n per player. So this bad equilibrium is n times worse than the good equilibrium. So that's an example of a kind of game that can have equilibria, the sum of which are kind of a lot better than others in terms of how much people pay. I like fair cost sharing because it can model a bunch of different things. Like, imagine a bunch of people trying to go from their houses to some common destination in the city. They could either, say, drive a car that, say, has some cost 1, or they could share some sort of shared transit. They could all agree to pay into some pool for some shared transit, and say that, typically, like if they're going to share something, that thing might be more expensive individually. Okay, I mean, it's not cost effective to be the only person riding a bus, but with a lot of people on it, it's worth it. So it could be individually more expensive, but if everybody uses that, a lot cheaper. So one equilibrium is everyone drives a car to work. A different equilibrium is we all share a bus. The second one is sort of better in terms of overall cost. But if everyone else is driving their own car, I don't want to be the only one paying for the, let's say that the way the bus works is, it just takes the cost of using the thing and split among the people using it. Okay. So there are notions of price of anarchy and price of stability. Price of anarchy is the ratio of the worst Nash equilibrium to optimal. Price of stability, the ratio of the best Nash equilibrium to optimal. And this game is sort of interesting because it always has a good equilibrium whose cost is only log n times worse than optimal, whereas it can have equilibria that are a factor of n worse than optimal. So this is the kind of game where you could have good equilibria and bad equilibria. There's been a lot of effort understanding these. So I think maybe what I'm going to do, since some kind of at the end, I was going to talk about, so these are potential games. Potential functions are really interesting. So for cost sharing, so it's the proof, like why the heck does this have the property that there's always an equilibrium within a log n factor of optimal? It's because this is a potential game that has, where the potential is a nice property. But maybe I'm not going to go through this. Okay, well, maybe I'll partially go. So, what is the heck is this game doing? If you have a state and there are a bunch of people using a particular edge, then each player using the edge, they split the cost. The total cost summed over all people is you're just paying for the edges being used. You're now splitting them among the people, but each edge is being used by at least one person, gets paid for. It gets paid for, it just happens to be split among those people. So the total cost of a certain state, a certain set of people using some edges is just, you look at the edges that at least one person is using and add up their costs. There's a thing called the potential function where instead of adding up their costs, you add, if there's 7 people using this edge, you add c plus c over 2 plus c over 3 plus c over 4 plus c over 5 c over 7. You add that. That quantity, I'm calling a potential function, that quantity, okay, why am I doing that? I'll get to over here, but that quantity is clearly greater than or equal to the cost, because CE plus some stuff, and it's at most log n times the cost, because we know that 1 plus a half plus a third plus a fourth up to 1 over n is at most log n, or h of n. It's log n plus 1. This thing has the amazing property that it's an exact potential. It has the amazing property that if a player moves, this thing changes by exactly the change in that player's cost. Okay, and that's what means to be an exact potential. You can kind of see that by staring at it. I don't have enough time to really go through here, but if you, I claim that if you spend, 20 minutes staring at this thing, and you say, what happens, if one player moves? So they move from something else. So, how much did their cost change? And you look at what this thing changes. This changes by exactly the amount that they change, which is sort of an amazing thing. And that's what makes this an exact potential. In particular, what this is the reason why best response dynamics will get to an equilibrium, because best response dynamics means if anybody is not happy, well, move. And if their cost goes down, so this thing goes down. Anyone not happy, well, then move. Their cost goes down, this thing can't go down forever because it's a non-negative number. And so it's got to hit a minimum. So the reason why there's always got to be a good equilibrium is you could start from the optimal behavior, run best response dynamics from that. This quantity only goes down. The cost might go up. But since the potential is bounded between the cost and log n times the cost, that potential is going down, the cost can go up. They can't cross each other. And so the cost can go up by most of this log n factor. So that's why this has that property. Okay. So one thing it says, if you could tell everybody to play the optimal behavior, and then from there they all went along, and then did best response dynamics from there, that would lead to a good state. And kind of an interesting model, let me not talk about it more generally. So an interesting model, I just want to define the model, I won't say anything about it, but it's to think about something we're calling the public service advertising model. It's sort of as follows. We imagine that players begin some arbitrary configuration. An authority launches some campaign. They say, hey, it's good to ride public transportation. So they propose some joint action that would be good to do. Each player looks at this, and with some small probability, they decide to pay attention. And some remaining probability, they don't. So some players are receptive. They want to do well. They want to do good. They like, when they see these ads, they say, oh, yeah, I guess you're right. Some small random fraction of people do that. And they do it for a while. The remaining other players just fall to an arbitrary equilibrium, or maybe they just do best response for a while. And then at some point the campaign wears off and people say, I don't want to be a patsy, and they just, from there, they all follow best response dynamics from there. And the question is, if you're stuck in some local optimum here, is this small fraction of people temporarily paying attention to this thing enough to sort of move you over the hump, so that from then on the best response dynamics can get you down to a good state? Okay. If everybody paid attention, that would be great. You would just pick the best equilibrium, say, hey, everybody do this. We're a totalitarian state. You got to do it, or you'll be killed. And then they would do it. But the thing is, we're not. All we can do is suggest things, and some fraction people might do it. And is it, if 10% of people follow along, is that enough to sort of pull everybody else? And the other thing is, technically, this issue of falling to an arbitrary equilibrium in a potential game, it could take quite a while to actually reach an equilibrium, but you can replace that with a polynomial number of steps of best response. Okay, and then given that, you can actually get some nice bounds for cost sharing. So I'm not going to go through proof. I'm just going to end. You can do a more learning-based model, or rather than having two classes of players sort of individually, say, flip coins, decide whether to do the proposed action or do best response, and maybe use a learning rule like randomized weighted majority or any other learning rule. As long as it goes slowly, changes the probability slowly, you can try to get them to work, and so you can analyze that as well, and then say what happens to the overall state of the system, and you can get some nice guarantees for cost sharing in this model. Okay, so let me just end saying, so regret minimizing algorithms give good performance against arbitrary sequences, and you can also talk about converging to the set of correlated or coarse correlated equilibria. On the other hand, there is this issue that I think is just worth keeping in mind, that if you're in a game where others are reactive to you, then there are issues that maybe had you behaved differently, the sequence would have been better. Right, so the case of good equilibrium and bad equilibrium is a little bit like that. Had I been nicer, they would have been nicer back, that kind of thing. That's not captured in this notion. It's interesting to consider natural dynamics that maybe can do better by knowing more about the structure of the game being played. These regret minimizing algorithms are great. In one sense, they are very general. You can run them knowing nothing about the game you're doing. You just try something, you just get feedback. You don't know what everyone else's motivations are. But if you did know more, maybe you could do better. Okay, that's it.
Questions?
for